At 1446 Japan Standard Time, on March 11, 2011, a magnitude 9.1 megathrust earthquake displaced the Pacific seafloor by up to 50 meters horizontally and 10 meters vertically along a 500-kilometer rupture zone. The sudden uplift transferred gravitational potential energy into the water column above, generating a deep ocean wave with a wavelength exceeding 200 kilometers. Within minutes, offshore pressure sensors recorded the approaching wave train moving at 800 kilometers per hour toward a coastline defended by the most sophisticated tsunami barrier system ever constructed. Japan's coastal defense infrastructure in 2011 represented the culmination of decades of engineering refinement following destructive tsunami events in 1896, 1933, and 1960. The Kamaishi Bay Breakwater, completed in 2009 at a cost of $1.5 billion USD, stood as the world's deepest tsunami barrier. Its two arms extended 2 kilometers into the bay, with caissons founded at 63 meters below sea level. Each reinforced concrete section measured 70 meters wide and rose 6 meters above mean high water. The structure was designed to attenuate wave energy for events up to the historical maximum, a 10-meter inundation height based on the 1896 Meiji Sunraku record. Coastal municipalities installed 10-meter-tall reinforced concrete seawalls backed by extensive drainage networks and automated floodgate systems. The design basis assumed a maximum wave period of 20 minutes and a total event duration of 2 hours. All structures incorporated factors of safety derived from probabilistic seismic hazard analysis calibrated to a 100-year return interval. The Tohoku earthquake originated at the Japan Trench subduction interface, where the Pacific plate descends beneath the North American plate at 83 millimeters per year. Accumulated strain released instantaneously across a fault plane measuring 300 by 150 kilometers, with maximum slip displacement reaching 50 meters near the trench axis. The rupture propagated bilaterally at 2.5 kilometers per second for 150 seconds, generating seismic waves that saturated accelerometers across northern Honshu. The vertical seafloor displacement imparted momentum to the entire overlying water column, creating a tsunami with energy proportional to the product of displaced volume and gravitational acceleration. Unlike wind-generated surface waves, this disturbance extended to the ocean floor, producing orbital water particle motion through the full depth. The initial wave traveled as a shallow water wave despite deep ocean transit, with velocity determined by the square root of gravitational acceleration multiplied by water depth. At 1449, 3 minutes after the main shock, the Pacific Tsunami Warning Center detected the event and issued alerts based on seismic magnitude. Japan's dense oceanographic array for earthquakes and tsunamis recorded pressure anomalies at offshore stations by 1455. The first wave crest arrived at GPS buoys 50 kilometers offshore at 1512, showing amplitude of 6 meters above baseline in open water. Coastal municipalities activated evacuation protocols and initiated automated closure of 300 floodgate installations. At the Kamaishi Breakwater, the arriving wave began diffracting around the structure's seaward terminus at 1521. Hydraulic modeling had predicted 60% wave height reduction for design basis events. The arriving wave measured 13.7 meters at the breakwater line, exceeding design parameters by 37%. 13 of the northern sector's automated gates failed to achieve full closure due to power interruption from the earthquake. The southern sector gates closed, but immediately experienced overtopping as the wave crest height exceeded the 6-meter freeboard by 7.7 meters. The initial wave transit time from offshore detection to coastal impact was 26 minutes. The wave train consisted of multiple crests with periods ranging from 35 to 58 minutes, substantially longer than the design basis 20-minute assumption. Hydraulic pressure persisted for 14 minutes during each wave crest passage, allowing sustained force application to seawall foundations. The receding trough phase generated seaward flow velocities exceeding 10 meters per second, initiating scour processes at structure bases. Foundation soils experienced cyclic loading as successive waves arrived at 40-minute intervals. Pore pressure buildup in sandy substrates reduced effective stress and bearing capacity. At Miyako, the fourth wave crest at 1643 produced the maximum run-up of 40.5 meters above Tokyo Peel datum. The extended duration prevented drainage systems from evacuating inundation between wave arrivals. Water levels behind seawalls remained elevated, eliminating hydrostatic pressure differential that would normally stabilize the structures during trough phases. Seawall failure initiated when hydrostatic pressure gradients exceeded the structural capacity of reinforced concrete sections. The Kamaishi breakwaters southern caisson chain experienced catastrophic failure at 1528 when horizontal water pressure reached 2.4 meganewtons per square meter against surfaces designed for 1.6 meganewton maximum loading. 6 caissons displaced from their rubble mound foundation, rotating seaward and fragmenting. The northern arm remained partially intact but allowed 70% wave transmission through the breach. At Taro, the 10-meter double seawall system collapsed when foundation scour undermined the base of the primary wall. The concrete structure failed in flexure as cantilevered sections exceeded their moment capacity. Failure propagated along 800 meters of wall alignment within 4 minutes. Similar cascading failures occurred at 47 coastal protection sites between Miyako and Soma. Post-event analysis identified that actual wave heights of 15 to 19 meters imposed forces 2.8 times greater than structural design values. Reinforcement detailing adequate for static loads proved insufficient for dynamic hydraulic loading and foundation instability. The Fukushima Daiichi nuclear power station occupied a coastal site with reactor buildings at 10 meters above mean sea level and critical emergency equipment at 4 meters elevation. Tsunami waves arrived at 1527, overtopping the station's 5.7-meter seawall and inundating the turbine buildings. Seawater entered through cable and pipe penetrations in below-grade structures, flooding the basements housing 13 emergency diesel generators. The generators provided backup power for reactor core cooling and spent fuel pool circulation following the earthquake-induced loss of off-site electrical supply. Within 40 minutes, 12 of the 13 generators failed due to seawater intrusion into fuel supply lines, cooling water systems, and electrical switchgear. Loss of AC power disabled the residual heat removal systems for reactors 1, 2, and 3. With the ultimate heat sink compromised by seawater flooding of the service water pumps, decay heat from the reactor cores began raising coolant temperatures. Battery-powered isolation condensers and reactor core isolation cooling systems provided temporary heat removal for 8 to 14 hours before battery depletion. The tsunami destroyed 78 bridges along National Route 45, removing entire span sections and displacing approach embankments. The Sendai Airport terminal flooded to a depth of 3 meters, with the wave transporting aircraft fuselages 200 meters inland. Runways sustained surface damage from debris impact and foundation settlement. The Senseki rail line suffered 43 kilometers of complete track removal, with ballast and ties scoured the bedrock in coastal sections. Port facilities at Kamaishi, Ofunato, and Ishinomaki lost all cargo handling equipment and berthing structures. Container cranes toppled and reinforced concrete wharfs fractured along their longitudinal axes. The wave transported fishing vessels up to 2 kilometers inland, depositing them in agricultural areas and residential zones. Highway overpasses experienced pier scour and bearing displacement. At Rikuzen Takata, the entire downtown district disappeared, leaving foundations exposed. Post-tsunami aerial surveys documented complete removal of buildings to bare concrete slabs across 470 square kilometers of inundated terrain. Emergency response operations faced immediate constraints from infrastructure destruction. The Ground Self-Defense Force mobilized 107,000 personnel, but encountered impassable road networks requiring 72 hours to establish initial access corridors. Debris fields containing vehicles, building materials, and marine equipment blocked primary routes. At Fukushima Daiichi, radiation releases from the damaged reactor cores established exclusion zones, preventing conventional recovery efforts. Contaminated water accumulation in the turbine buildings and trenches required continuous management. The combination of physical debris and radiological hazards prevented direct access to failed cooling systems for 96 hours after the event. Search and rescue operations in coastal zones proceeded without heavy equipment for the first week due to road obstructions. Temporary ports required construction before maritime supply lines could be established. The lack of electrical power across the affected region eliminated pumping capacity needed to drain flooded areas and confined spaces. Final inundation height surveys documented maximum run-up of 40.5 meters at Omoe Peninsula in Miyako. The tsunami completely destroyed 120,000 buildings and partially damaged 280,000 additional structures across 6 prefectures. At Fukushima Daiichi, cooling system failure led to fuel damage in reactor cores 1, 2, and 3, with hydrogen explosions destroying the secondary containment buildings for units 1, 3, and 4. Spent fuel pool water levels dropped below fuel assemblies in Unit 4 before emergency water injection restored cooling. The station released 940 petabecquerels of iodine-131 and 12 petabecquerels of cesium-137 into the environment. Evacuation zones encompassed 160,000 residents within 20 kilometers of the plant. Power restoration to reactor cooling systems required 10 days for Unit 1 and 17 days for Units 2 and 3. The total economic impact reached $360 billion USD, including infrastructure reconstruction and agricultural contamination remediation. The National Diet of Japan Fukushima Nuclear Accident Independent Investigation Commission released its findings in July 2012, identifying the tsunami flooding of emergency power systems as the direct cause of the nuclear accident. The commission determined that the 15-meter wave height exceeded all facility design calculations based on historical records and deterministic modeling. The report mandated elevation of emergency generators and electrical distribution equipment to 20 meters above sea level at all coastal nuclear installations. The Ministry of Land, Infrastructure, Transport, and Tourism initiated construction of the Great Forest Wall, a 400-kilometer system of elevated earthen berms reinforced with deep-rooted vegetation to attenuate future tsunami energy. Revised coastal defense standards incorporated 34.6-meter design wave heights derived from probabilistic maximum tsunami analysis. The reconstruction program allocated 25 trillion yen to seawall elevation, relocation of 40,000 residential structures to high ground, and hardening of critical infrastructure against 1,000-year return interval events.